Here's a general strategy that you can use to solve problems dealing with gases. Okay? Typically, in a lot of these cases, you're not going to have enough information to just plug things into PV equals nRT. So when you read these problems, you sort of have to get a picture of exactly what's going on with the gas. Okay? And so what you need to do when solving these problems is you need to identify what is being held constant. So identify the constants in the equation PV equals nRT. So if you can tell that N and T, the temperature is constant and you have a fixed amount of gas, then you know you're dealing with Boyle's law. P1 V1 equals P2 V2. If you know that the pressure is being held constant and you have a fixed amount of gas, then you know you're dealing with Charles's law. So uh, the simpler equation to use would be V1 over T1 equals V2 over T2. And if you're holding volume constant for a fixed amount of gas, then you're dealing with the effect of temperature and pressure. That's Amundsen's law. P1 over T1 equals P2 over T2. Okay? Now, if the problem, based on the way the problem is worded, it appears that only the amount of gas is held constant, that you can have pressure, volume, and temperature can actually change, then you have to use what's known as a combined gas law. Where do we get this one? PV equals nRT, so only N is constant, right? So R is also a constant, so you divide both sides by T to put all your variables on one side. So you say PV over T is equal to NR, and this is a constant. So if only N is constant, then PV over T is a constant, so you say P1 V1 over T1 equals P2 V2 over T2. This is also known as the combined gas law. Okay, we're going to look at an example of that in the next slide. Now, if two of these things, P, V, and T, if two of these are held constant, then the only way the other one could change is if you actually have a change in the number of moles. We're going to deal with that in the next lesson. So if you have constant T and P, or V and T, or V and P, okay, then you can say that the other variable, the remaining one, would be related to the number of moles of gas in your sample. So you must be dealing with cases where the number of moles of gas have changed, and that's in another lesson, okay, in the next lesson. But for now, let's take a look at an example of a problem that involves the combined gas law. Here's one. What's the final volume of the gas? Originally at 30 liters, 250 torr at 25 degrees Celsius. If its pressure and temperature are changed, so you're changing both pressure and temperature, okay, and you're looking for the final volume. So you have P1, V1, and T1. Originally, you're changing it to P2, V2, and T2. How do you know that the gas here has a constant N? Based on just reading this problem, you're assuming here, we can assume here that you have a constant number of moles of gas. Well, you can say, it says volume of a gas. It doesn't say anything about doing anything to the moles of gas in there. It's not, you're not putting any extra gas in there. You're not taking any gas out there. You're just changing the volume and temperature. So, absent that additional information about the change in moles, you can assume the number of moles is constant. Okay. Now, if you had something like maybe something like you have a gas in an open container, and you're told you heated the gas, and what happens to the pressure of the gas, then you could imagine that the gas molecules can leave your system, and so leave that container, so that the number of moles of gas might not be constant. So if your container is open, then that's something that you can't assume that your N is constant. All right. So anyway, let's solve this problem. What do we have here? We have P1 V1. So you have to use the combined gas law here. P1 V1 over T1 equals P2 V2 over T2. What do we know? And what are we looking for? We're looking for the final volume of the gas. So we just solve for V2, rearrange this equation. What do? We multiply both sides by T2. That gets rid of T2 from that side, where the V2 is. And you divide both sides by P2, so you can get rid of P2 from the right side. Okay, so now what do I get? I have V2 is equal to this thing on the left, which I'm going to rearrange. Okay, I'm going to say that's equal to V1 times T2 over T1 times P1 over P2. Doesn't really matter which order you do them, right? Multiplication is commutative. So, but I like to do it that way, this way. That way I won't have to worry too much about my units. They'll just cancel out when I have T2 over T1 and P1 over P2. So what's my V1? My initial volume, according to this, is 30 liters. 30 liters. T2 over T1. Let's see, what's T2? Final temperature is 115 Celsius. Initial temperature is 25. Now, be careful here. 115 degrees Celsius, I have to change that to Kelvin, so I have to add 273, right? And my initial temperature is 25 degrees Celsius, so I have to change that to Kelvin, so 25 plus 273. And so Kelvin up here, Kelvin down here, Kelvin cancels out. All right? And then finally, I multiply that by P1 over P2. So P1 is 250 torr. And P2 is 500 torr. Okay? So if we did that, so I have 30 times, let me get my temperature factor first. Okay, so parenthesis, 115 plus 273, close parenthesis, divided by, parenthesis, 25 plus 273, close parenthesis. That ratio is 1.302. You can see I'm multiplying my original volume by 1.3. I'm making my, what's the effect of raising the temperature? To make the volume increase, right? So that makes sense. And then this is, of course, 250 times divided by 500 is 0.5. So what am I doing here? My initial volume, I multiplied by a number greater than 1 because my temperature went up. And I'm multiplying it by a number less than 1. A number less than 1 because I raised my pressure. Okay? You raise the pressure, the volume shrinks. You raise the temperature, the volume expands. So the original volume, V1, is multiplied by a temperature factor greater than 1, is multiplied by a pressure factor less than 1 to get the final volume. So I have this 1.302 times the original volume, which is 30, times the pressure factor, which is 0.5, and so I get 19.5 liters. Okay? So correct answer here is 19.5 liters.